Well, let's get started. So we're going to talk about logic some more, and then also like the idea of a frame of reference when you're making an argument. So that'll be fun. So I want to teach you like cold hard logic, the kind that computers are good at, and the kind that humans are good at too. There's two kinds of logical, not formulas, but ways of logically thinking. There's deductive logic and inductive logic. All right, so the verbs are like, those are the verbs, and like the nouns are deduction and induction. All right, so computers are super good at this thing called deduction, and humans are awesome at this thing called induction, and like slowly but surely ChatGPT is getting better, but it's still not quite there. Right? Humans are still the best at this thing. Computers are great at deduction though. So what's the difference? And these are different ways to like think about things and formulate arguments. So we're going to try and answer this question to like what makes an argument right, correct, a good one. All right. So that's going to be helpful as you're writing future essays. So that's exciting. So deduction, the thing that computers are good at, looks like this. These are examples of deductive arguments. Okay. So in general, any argument that anybody writes ever is made up of some pieces. All right. The pieces that make up every argument are called the premises or premises. And then there's a final conclusion based on the premises. All right, they're trying to like provide firepower to give you that conclusion. Right? Premise is just a synonym for assumptions. Like your argument, it revolves around some assumptions, and then based on those assumptions, you're concluding some final thing. Okay, that's the goal. So an argument we say is deductive. Every argument looks like this, but a deductive argument is a special one that has premises and a conclusion, and we call it deductive when the conclusion is a certainty based on those assumptions, based on those premises. All right, so just like imagine this, like imagine we have some argument. My arguments will be in cloud shapes. All right, so we got some premises that are like being used as firepower towards our conclusions, like premise 1, assume that. Premise 2, assume that cloud of an idea. Premise 3, assume that too. And then the goal is that all these premises, they work together to imply, that's the fancy word, to imply a conclusion, all right? That's the thing you're trying to get at and convince somebody of, okay? And that, in a deductive world, if this is a deductive argument, based on these assumptions, if you assume them, the conclusion will always be true, all right? And that's what it means to be a good deductive argument. Conclusion, it will always be true. The premises will always be enough to let you conclude your conclusion. All right? So that doesn't make a lot of sense right now, I know, but just like listen to my words, and then with enough examples, I think it'll make sense. Here's a good deductive argument that will try and drive this point home. Okay, so there are two premises to this argument. Before I even talk about it, there are two premises, and they're trying to be used as firepower towards some final conclusion. All right, that's the main thing I'm arguing. All right, so premise 1, which is true today. It is sunny in Fresno, all right? That's first premise. So assume that, okay? Premise 2, if it's sunny in Fresno today, then Lawton will not be carrying an umbrella because normally people carry umbrellas during rainy days. I guess that's not actually accurate because I started carrying an umbrella when it's really hot. But still, assume that, right? So assume this is true. Assume it's sunny in Fresno. Even if it isn't today, assume it's true, okay? That's what we're doing. Premise 2, if it's sunny in Fresno, then Lawton won't be carrying an umbrella. So those are the two things, right? We're assuming those, even if they aren't really true. Doesn't matter. And then our conclusion, based on those premises, is like, all right, what we will conclude is, therefore, so Lawton will not be carrying an umbrella today. Okay? And this is a deductive argument, and it is a good one, right? Because under these assumptions, do you see how, like, you can kind of plug this fact into this if-then? Like you get out this, like if you were to assume that those two things are true, like you can feed the first into the second and it will spit out the conclusion, which is a correct way of thinking. Yes? Does that make sense? Even if those premises are weird, you're just assuming that you live in a universe where they're true. Okay? That's kind of how we think. Right? But yeah, this is a deductive argument and it's correct. The conclusion is a certainty based on these premises. Assuming they're true, this conclusion must be true. Right? Any questions about that? That's a weird concept. I'll show you some more examples though later. That's kind of the idea. An argument is deductive when the conclusion is a certainty based on those premises. You just assume you're in a universe where those premises are true. And if they imply that conclusion and it works out, and it's always true, no matter what, then it is a deductive argument. Right? And that's something computers are very good at. They're good at plugging things into other things and getting out final answers. That's a kind of a robotic task. Right? So computers are great at that. Induction is what humans are better at. I guess slowly but surely with these new AI tools, computers will also get better, but they're still like hallucinating, right? So let's talk about induction. It's kind of the opposite of deduction. There are some other words, there are some other things called induction in the world, like maybe if you're a math major, you've heard of like mathematical induction, if you've taken computer science 26. It's not that, all right? It's a different kind of thing. We're talking about arguments right now. So an argument is inductive when the conclusion is super likely. It doesn't have to be a certainty like it did with deduction. It's just it's very likely based on your premises. So induction is just a game of probabilities, really. Probabilities, okay? So that's the goal there. So here's an example inductive argument. Again, the conclusion will be like we're trying to prove this, we're trying to argue this based on a premise, like we're assuming this, then trying to show this is always true, or is sometimes true, is very likely, essentially, for induction, okay? So, okay, here's the premise. Every time I walk by that scary dog, it hasn't tried to bite me, okay, even though it's scary. So that is my assumption, that's my premise. I've collected data, right? Every time I walk by that dog, it has not tried to bite me. And so I will conclude, right, therefore, so next time I walk by the dog, it probably won't try to bite me, right? It hasn't yet, so it probably won't. Does that make sense? Do we see the difference? It's not a certainty. It's just super likely. Like maybe the dog's having a really bad day or something, and like it ends up wanting to bite somebody. But it is a very likely conclusion. It is not a certainty, though. Okay, and so these are the kinds of probability games that we play in our head all day long. Right? We're making these arguments. If I do this, this will probably happen. If I do my work, I'll probably get a good grade. Yeah. So probably is the key word here. Do we kind of see the difference between like this is a certainty based on these assumptions? There is no wiggle room. Versus this is just like given the data, it's likely that this is the case. Okay, that's the difference between deduction and induction. Are we good with that? I'll give you some questions of that in a second to drive it home. But now that we know what arguments are, they look like either they look like this or they look like this, more or less. And let's try and prove whether they're good arguments. Okay, let's talk about. I think this is really only going to apply to deductive arguments, but you can sometimes squeeze these words into inductive ones. But let's shift our focus back to deductive arguments because they're easier to think about. This is a certainty based on the premises. All right. So let's talk about validity and soundness. Those are two ways to describe a deductive argument. All right, and you want both usually. Soundness, by the way, it's stronger than validity. So stronger than validity. So if you have a sound argument, that's the best kind. Stronger than validity. If you have a sound argument, it's automatically a valid argument. All right. So they're two nice adjectives, and when we learn about them, it'll be useful for us to fight back with other people who are arguing things. So we can attack their arguments. We can say, "Oh, your argument is not valid. Your argument is not sound." So I'll give you some tools in that way. All right. So let me show you an example of a bad argument. All right. So here's a silly little setup scenario. It's got two premises and a conclusion. So here's one premise, here's another premise. They're trying to be used as like firepower to imply this conclusion here, like bring them together and give us that conclusion. Sometimes people draw a line like this between the premises and the conclusion. But here's my silly little scenario. I had ChatGPT come up with this little idea. I think it's funny. So okay, here's the deal. In the quaint town of Deauville, renowned for its delightful bakeries, a peculiar incident unfolded that led to the arrest of an innocent citizen. So this is not good. All right, we have to fix this. The town was abuzz with excitement over a mysterious theft of the mayor of the town's prized golden muffin, which he kept locked up. It was a priceless artifact handed down through generations of mayors of Deauville. Okay, this is my silly story. The cops, they received an anonymous tip last night suggesting that the Muffin Man, that wonderful pastry chef, right, was the prime suspect in this crime, right, for stealing the golden muffin. the tipster, who like called in to the hotline or whatever last night, claimed to have witnessed the baker near the mayor's residence on the night of the theft. They're like, okay, based on that, all right, silly story, here's what we know, all right? The golden muffin, it was stolen from the mayor's residence last night. We'll assume that, right? We know that that is true. All right, the muffin man was seen near the mayor's residence on the night of the theft. Okay, we got those two things together. And then this was the argument that the police made. They're like, all right, therefore, the muffin man must have been the thief who stole that golden muffin. Okay, and then they locked him up. And now an innocent person is in jail right now, right? Potentially. So what's wrong with this argument? Like, these are two assumptions, and this is the conclusion we're trying to conclude. Why doesn't it work? Good. Yeah, can somebody or you, could you expand on that? Should be a little bit more precise. Good. What's the word? I'm not a lawyer, but it's not situational, circumstantial evidence. It's not. You have nothing concrete, right? You don't have anybody like with a video camera showing the muffin man actually stealing this thing. Okay, so there's an issue here, right? These ideas, these two ideas, sure they're true. They don't give you this always, right? Thinking about the word always right now, kind of Kantian in this sense, right? So can you always conclude that the muffin man, based on these two ideas, that the muffin man was the thief for sure? Absolutely not, right? Maybe the real thief was better at hiding themselves, and they took off like in a helicopter or something. I don't know. There's a lot of holes in this story, and this is circumstantial evidence, and so it's not good that that the cops went and locked away the muffin man. It's not a correct way to conclude that he was the thief. All right, so this is an example actually of an invalid argument. Invalid. All right, it's an invalid argument. Let's see, what's the best way to talk about that? Yeah, so it's invalid because these two guys, they don't give you this, and I'll define validity soon. But that's an example of an invalid argument. I hope you can kind of see it breaks down, right? It was not logical when we thought about it. Okay, so let me show you an example of an argument that's valid but not sound. All right, so here's a silly argument. Again, we've got two premises and a conclusion. They're trying to be used together to give you this. Okay, so here's an argument. All right, assume premise one: all people with a GitHub account are successful programmers. If you don't know about it, GitHub is a website. That's actually where I'm posting our code from class. It's just a place that you can host code that you write just for free on the internet. So let's assume that all people with GitHub accounts are successful programmers. All right, and some dude named John has a GitHub account. So assume those two things. All right, and we want to conclude, therefore, John is a successful programmer. Okay, so do these two assumptions together give you this? Does that work? Is there anything wrong? I think it does work out, right? Because if you assume you live in a universe where this is true, right, you can plug John in because he's a person with a GitHub account, and it'll spit out that John is a successful programmer. Yes. So do you see how that will conclude what we need to conclude without it beyond a shadow of a doubt? So that is a valid argument, we'll say. All right, it's valid, but is there anything wrong with assuming any of these things? Anybody see it? Maybe John does have a GitHub account, that's fine. What's wrong with the first assumption? Yeah, do we live in a universe where that's actually true? Probably not. There's plenty of starting out students that have GitHub accounts. They're not successful yet, right? So this casts a shadow on our whole argument, right? So we have some doubts about this being true. Yes. So it's valid if we were to assume that we live in a universe where that is true. Both of these things taken together, you can plug this into that, and it will spit out this. So it's valid, we'll say, but it's not sound, right? Because this assumption is it's silly. Yeah, that's the idea. Valid, but unsound. And that's the secret. And those letters look the same. All right, so those are ways to attack arguments now. So, okay, let me actually spell it out. So we've kind of noticed this is what's going on. We got some premises usually. A lot of the time we have like one premise that looks like thing A is true, and then premise the other one is like if thing A is true, then thing B is true. And what we were doing was we're trying to like plug A into that one, like it'll spit out the B. That's the game that we're playing. That's what it means to be a deductive argument usually. So here are those words now actually defined. So an argument we say is valid if it's impossible for the premises to be true and the conclusion to be false. Right? So that just means it's a good deductive argument. We say it's valid. Given these premises, assuming we live in a universe where they're both true, the conclusion is always true. It's impossible for it to not be true based on those assumptions. Okay? So like this was an invalid argument because these two assumptions taken together does not give us this, right? Could have been somebody else. There's room. All right? Whereas this one was totally valid because these two things together, you plug the second one into the first one, it will give you this final thing. Okay? So it's valid. So that's what it means to be valid. Sound is this. So an argument we say is sound if it's valid. So it's got to be valid first. And some additional things. We also want all the premises to actually be true in this current universe. Okay? That's the idea. So, yeah, the second is not valid, it cannot be sound. But if you have a valid argument, it's possible that it is an unsound argument. You look at the premises and be like, all right, is this true? Do we live in this universe? Let's assume that yes, sure. John does have a GitHub account, probably. And then we look at this one, criticize it, right? Is this actually true in the world? Does everybody with a GitHub account, are they successful programmers? And no, there's plenty of early students that have one thing on GitHub and they are not successful yet. Okay, so that is the idea of soundness. It's valid, and all the premises are true. All right, so those are the fancy words that you can use to attack people's arguments now. All right, you can kind of break it down into this way. Look and see, look into their argument. What are the things they're assuming? What are they trying to conclude? See if it's valid by seeing if those premises actually give you that conclusion, always. And then see if it's sound by checking, hey, do those assumptions actually make sense? Are they true in this universe, this current universe right now? Okay. So those are the terms. Any questions about any of that? All right, so I want you to try it out. So I'll give you these definitions all over the place. So just keep pasting it, I guess. But here's a silly argument. Let me break it down for you, and then we're going to have a bunch of these. Okay, so here is an argument. All birds can fly. Bats are birds. Those are your two assumptions, if you think about it long enough. Those are those two things. Assume those. Therefore, conclusion, bats can fly, right? All birds can fly. Bats are birds. Therefore, bats can fly. All right, so that's the argument. Please tell me, is it valid, sound, both, or neither? Get into groups. Look at these think back to the examples. Look at this definition. And please answer on the by clicker page once you've convinced your neighbors that you are correct. All right? And make sure to do attendance. I'll stop that after the first question. All right? So please help each other and try to see if you can figure out what is true about this argument. Valid, sound, both. The assumptions. You're the right words. Good. Give you another minute to think about it. that's pretty much my timer. Is that enough time to discuss? Are we still thinking about it? Not sure yet? Okay, yeah, try get your guesses in right now, even if you didn't get it. If you're not sure. It's a little tricky once you first learn it. Yeah. So I don't expect you all to get it right. That's why we're having a lecture on it. And I'm going to give you more examples, more questions. This is like rapid fire. So yeah, let's see what we're thinking. Whee! Did I click it? There we go. Nice. Ooh, look at this. All right, we're thinking slight majority. Very, very slight majority A. Definitely not B, which is good, right? It can never be sound only. The second it's sound, it's also valid. So very good that we noticed that it could not be B. It is going to be A. So let's see. Can somebody describe, somebody who picked A, that is going to be the answer. Can anybody explain to me why that is going to be the answer? Like, that just seemed like the right one. Just on vibes alone. Gave us that. That's true. That's true. So that means it's not sound. Yeah, we'll get to that. But why was it valid? Okay, because it could have been neither, right? Could have been neither. So it's valid when like these two taken together give you this, and it's certainty with certainty, right? It's impossible for this like these to be true and this to be false. So all right, we're assuming we live in a universe where all birds can fly. We assume we live in a universe where bats are birds. Can you conclude, therefore, like can you like use these together to conclude that bats can fly? So that's what it means to be valid. Sure, because if bats are birds, you can plug bats into this, right? We get out that all birds can fly. We're just assuming those things. And if a bat is a bird, it can fly. Therefore, that's exactly what I'm trying to conclude. Do we see how it's valid because of that? You can use those assumptions to always, with certainty, get that conclusion. Under these assumptions, we pretend we live in a universe where these are true. We're trying to get this out, and it does work. Okay, so that's what it means to be valid. Yeah, but it's not sound. So good that we noticed it wasn't sound, because can all birds fly? First of all, is that true? Yeah, you got like penguins, right? You can count or not. It depends. Depends on how long. Like chickens can fly for a little bit. Maybe they can glide, like emus and things. I don't know. Also, are bats birds? I had to look this up a couple semesters ago. Apparently, bats are mammals. Yeah, I didn't know that. I forgot. I did not take a biology class very recently. So, yeah, both of these actually are not true in this universe. But if we were to assume that they were, we do get this conclusion. So it is valid, but it's not sound. Okay? Any questions about this? Does it kind of make sense now? More so than before? Because yeah, I just want you to try a bunch of these. That's how you learn this concept. So let's start over again. Please get back into your groups. And here's another question for you. All right? Here's another kind of argument. All snakes are reptiles. All lizards are reptiles. Therefore, all snakes are lizards. Valid, sound, both are neither. a minute or so, get your answer, your best guess in. All right, let's see what we're thinking. It's converged. There it goes. All right. Oh, okay. Nice. With a majority, slight majority again, we're thinking D. Nice. Let's see here. So, yeah, you can actually see, you know it can't be B, right? Can't only be sound. It has to both be sound and valid. So your valid answer, your correct answers could only be A, C, or D. And if we're thinking it's D, let's just like make sure it's not A, right? Because if it's not A, it's not anything. Let's see. Is this an invalid argument? So like, all right, that means, does it mean that, all right, these two guys, I want to be able to use them to like provide this. Is it going to work out? Can I somehow use these two ideas, these two facts? All snakes are reptiles, all lizards are reptiles, to get that snakes are lizards. Does that imply that? I don't think it does, right? Because kind of what these assumptions are saying is like, you give me a snake, I will tell you that that snake is a reptile. Like I have that fact for you. That's kind of what the first thing is saying. And then the second one is like, all right, you give me a lizard, I'll tell you that that lizard is a reptile. It's like, that's the arrow, that's the direction. And they were trying to use both of these to conclude that snakes are lizards, but it's like, that's the wrong arrow direction. Does that make sense? Like, you give me a snake, I'll tell you that these things are reptiles. I know that snakes are reptiles, but I know nothing about like how snakes and lizards are related, other than that they're both reptiles. Does that make sense? So it can't be valid because these two things do not provide enough firepower to give us this. There's no way to conclude it. Okay. So yeah, the second it's not valid, the only answer is neither, right? Because it can't be sound only, and if it's not valid, it can't be both valid. These are two true statements, though, so that might trip you up, right? Can't just be sound, though. It's not just. Let's see. All reptiles are snakes. Let's see. All reptiles are snakes. Potential. It might be the wrong direction again. Yeah, there's a way. There's a way to make it happen where you can like align things. Snakes, reptiles. I think it would have to be all reptiles or lizards, because then you could be like snake. You can go from snake to reptile and then reptile to lizard. Does that make sense? I think it would be the second one you'd have to move around, because that would give the arrow in the other direction. I hope that makes enough sense. Yeah, that's an interesting one, right? So that's why it can't just be sound. All right. How about this one? I'll try it again. Seems like we're getting at that. So here, try this, discuss, and see if you can get it right. So here's my silly argument this time. So every time Dave orders pizza, assume this, right? His neighbor Bob can smell that pizza from his house. Poor Bob is not getting any. And then assume that Bob smells pizza right now. Therefore, conclusion, Dave must have ordered pizza. Valid, sound, both or neither. Two assumptions, conclusion. All right, I think our words have died down. Take another couple seconds to get your answer or your guess in. What do you think? Am I tricking you? I'm trying not to trick you. This is just like, this is somebody's argument, right? Is it a good one or is it a bad one? We're trying to break it down, all right? Attack it. All right, let's see. Ooh, we are split. Look at us. Look at us. So, there is no majority anymore, but like the most of us are thinking A. Okay, let's see. Let's see. All right, we've got every time Dave orders pizza, his neighbor Bob can smell it from his house. All right. Let's try to break this down into this idea of like arrows, because that was helpful, right? So like, what's the arrow relationship going on here? So every time Dave orders pizza, so if Dave orders pizza, then we can conclude that Bob can smell that pizza. Yes, that's what that's saying. Bob smells pizza. Does that make sense? How I can change that into the arrow-ish form? Like, you give me this, I will get that out. Right? Dave orders pizza, then Bob can smell it. And then we have that Bob smells pizza right now, and we're trying to conclude that Dave must have ordered pizza. Right? Is this valid? Can I like plug this guy, this into this, and get this out? That's my question. And a lot of us thought yes. But I'm here to tell you that that would have only been possible if it was the arrow in that direction. Do we see the difference? This will only work out if I know that Dave ordered pizza, right? Then Bob will smell it. Give me that, I can prove to you that Bob will smell that pizza. But this is trying to run this arrow backwards. Bob smells pizza right now. I cannot conclude that it was Dave that ordered that pizza, right? It could have been some other neighbor, right? Just think about the options. Does that make sense? It can't be valid. It can't be valid because you're trying to run that arrow in the wrong direction. Yeah? This is like an if-then. If Dave orders pizza, then Bob smells it. So you need this to get this. You cannot go backwards. It's not correct to go backwards. If Bob smells the pizza, it does not mean that Dave ordered that pizza. Okay? Even though we have that, right? That's what we're trying to conclude. That won't work out. Because it could have been Bob's wife surprising him with pizza. Who knows? Right? That's the idea. So it can't be valid, which means it can't be sound, because it has to be valid to be sound. Since it's not valid, it's not both. So the only answer must be neither. Does that make sense? It's a trickier one. Okay? One last one. One last example. All right. Put it back up there. Hide, begin. Dun, dun, dun. Valid or sound. Here's our last argument. Assume all mammals are warm-blooded animals, and that dolphins are mammals. All right? And therefore, we're going to conclude that dolphins must be warm-blooded animals. Okay? That is my last argument for us to try. Valid, sound, both or neither. Did I click the restart button on the question? I do believe I did. Finish strong. Do those premises imply that conclusion? Are those premises actually true in this universe in which we live? that enough time? Let's see. Drum roll. Let's see if we all got it right. Look at us. All right, we're thinking with another slight majority. C. Nice. I think that's going to work. So this is finally both. Let's see why. So, okay, all mammals are warm-blooded animals. That's our assumption. So, all right, that's trying to say what's the arrow, right? What's my if then? If you give me a mammal, then I can show you that that is a warm-blooded animal. I have that fact for you, right? That is a true thing, right? If you give me a mammal, I will tell you that they're warm-blooded. That's what that's trying to say, right? I'll give you proof. And then, all right, dolphins are mammals. Trying to plug this, right, into this. Dolphins are mammals, and I know that mammals are warm-blooded, and therefore, dolphins are warm-blooded animals. So you see how that's going to spit out the answer that I want? So it is valid. Right? It is valid. Now the question is it also sound? Are all those premises true? Is it true that mammals are warm-blooded animals? I think so. Yeah, and then dolphins, they're definitely mammals. They evolved in some weird way, right? Like they were on back into the ocean. It's crazy to think about. But yeah, those are both true. So it's valid and sound. Isn't that fun? Can't just be sound, remember. These are true statements, but it can't just be sound. You have to also check for validity. It's not valid only. Okay? So yeah, nice work. I hope that makes sense. I think I promised to stop that. And any questions about that? I think we're getting it. Slowly but surely. Go back and study these. But this is a way for you to attack somebody's argument now. All right. Well, let's talk about that arrow because it was here a lot. What does that arrow actually mean? Can we give it a real meaning? Because that had to do with if, right? If this is true, then this is true, kind of thing. So obviously, we don't like using English when we're making our arguments, especially when we're like programming our arguments. It's like, what does that if really mean? Can we make it precise? All right. So here is. Let's break this down. Let's come up with a new logical symbol for if-then relationships. All right. So here's something Dad told me. All right. Say that Dad told us that. All right, I'll give you $20 if you mow the lawn. All right. So do you see how there is an if-then relationship? If you mow the lawn, right? If you do this, then you're getting this. Then I'll give you $20. It's kind of backwards, right? Does that make sense? So that's kind of the arrow. If this is true, give me that. I'll give you that. Yeah. You mow the lawn, I'll give you $20. It's an arrow in that direction. And so let's try to come up with like a mathematical symbol. We'll just use the arrow again. That means if and like make a truth table for it. So we're going to go to a truth table. We're going to have to figure out like when is it false? When is this if-then statement false? And when is it true? All right. So I told you before that false kind of means, I want you to think of it as like you were lied to. You feel cheated, right? Let's come up, let's write down all the possibilities of us mowing the lawn and Dad giving us $20, and we'll think about under which cases do I feel like I was lied to? Because that'll be the false case for my if-then logical statement. Right? We're going to try and formalize this. Under what conditions do we feel cheated if we didn't get $20? So here are all the different combinations of mowing the lawn. That's the first thing, right? The if part, and then the then part is the got $20 one. So right? Here are all the combinations of mowing the lawn and getting $20, right? And let's look at them all. So, okay, if we mow the lawn and we got $20, do we think that Dad lied to us? No, let's go. That's perfect. I got the money that I was asking for. Perfect. We're good to go. Thank you, Dad. I'll come back to the second one. If we didn't mow the lawn, but we got $20 anyway, do we feel cheated? Were we lied to? No, Dad was just really he was really nice to us today. We got our money for free, which is cool. So that's not false. Shouldn't be interpreted as false. If we didn't mow the lawn and we didn't get $20, do we feel like Dad lied to us? No, like we didn't uphold our end of the bargain, right? So in the only case where we feel like we got lied to is if we mowed the lawn, but we didn't actually get those $20, because then this statement, it's not a good, it was incorrect. We were lied to, right? We upheld our end of the bargain, but we didn't get those $20. So that's going to be the one case when we formalize this that is false, right? It's a false idea, all right? So let's make a symbol for if something, then something else. If A, then B. You can also tack along like if A is true. You can think about it that way. If A is true, then B is true. That's another way to think of it. Okay? True. So this is called implication. That's our mathematical if-then statement. It's going to be, some people use a single arrow, some people use double arrows. It's just like, it looks like this. You got your if side, you put an arrow, then you have your then side, all right? And we've just determined the truth table for this, all right? So implication is its fancy name. It's the logical symbol for an if-then statement. It's called a conditional in programming, right? It's going to give us true or false, one way or another. And so we just figured out its truth table, right? So pretend that A is mowed the lawn and B has got $20. Got $20. And then this is, if you mow the lawn, then you'll get $20. That's Dad's statement, right? If A, then B. All right, so this is our truth table. It is true, right? If A, then B, if you mow the lawn, then you get $20 is true in every case, except for the case where you mowed that lawn, but you didn't get the $20, right? That's the idea. It's true in every other case. Does that make sense? That's how we're going to do it. That's how we're going to make it work. It's true in all these guys. The only way to make it false is if you uphold your end of the bargain, but you don't get the conclusion out of the deal. That's the only time that that is false, okay? And so that's the one, if you're trying to prove, right? If you're Dad or something, and you're trying to prove that your if-then statement is true, you have to show that you cannot be here. You have to show that you're not in this universe. You have to show that if you have this part, if you've got the left side, if you've got the if side, you always also have the right side. Right? You must be in this one and not this one if A is true, right? Because the other one is just like automatically true. Okay? That's what you'll do when you're trying to prove the thing. So it's impossible to fulfill the if side and not get your benefit, the then side, right? That's one way to prove it. Alternatively, like how to prove, how will Dad prove to us that he's saying the truth in his if-then statement? Like, if I give you A, then you have to give me B. That's kind of what it's saying, right? In every other case, where I don't give you, or if you don't give me A, then I don't have to do anything. It doesn't matter, all right? I wasn't lying to you if you don't get what you wanted. Okay, so that is maybe a little vague still, but that kind of like pins down those arrows that we were using before. All right, we've given it an actual symbol. We've figured out when it's true and false. All right, so let's go back to deduction now, because we can talk about why deduction is like a very logical thing and it makes sense in a computer and it always works out. Right. So here is like the quintessential deductive argument. You'll see this in any philosophy class, or if you go on Wikipedia and look up deduction, this argument will be there. For some reason, that's the one everybody uses. So, all right, this is two premises and a conclusion. All men are mortal, assume that. Assume Socrates is a man, and we're concluding, therefore, Socrates is mortal, right? And so this is valid. This is valid because you can plug Socrates into this. Socrates is a man, all men are mortal. It will spit out that, oh yeah, Socrates, that one man, he was immortal too, okay? That's the goal. And so if we break this down into symbols now, I can prove to you with a truth table that this is a correct and valid argument, right? Why it's logical, it kind of works out. So do you see how this first thing is saying, like, if you give me a man, I will give you proof that they're mortal? That's how you can read that. So man implies mortal is another way to say it. So assume that that's true, right? Which means assume that you're in one of these cases, yeah? Assume that you're in one of these cases that make it true. That is interesting. That's powerful, right? So assume this is true, and then assume man is true, and then we're trying to prove that therefore mortal is true. If man, right? If man, then mortal. That's your A, that's your B. Okay? It's like assume this is true. Assume man is true. Then we're trying to prove that mortal is true. That kind of makes sense. So let me show you that this conclusion right here, the reason it's valid is because we can look at the truth table for both of these at once. And like we'll notice, like it's beyond a shadow of a doubt, there's only one way. Like mortal must be true. The B part must have been true. And that's how we can prove that this was valid. Right? So the conclusion. And I'll show you just a second. The conclusion. It follows from the truth table. Actually, for that symbol right there. So that's perfect. Okay? So that's the goal. Okay? So we're going to assume that if man, then mortal is true. So let's go back to this. So that means we're in either this one, or this one, because that's the only way that the A implies B is true. Assume that A is man and B is mortal. Yeah. So assume we're in one of those. Then also, what else? So assume we're in one of these guys. Then also assume that man is true. That's the A part, right? So which sides were we on if A is true? So assuming that we're in one of these right now, in this one, or this one, where is it also that A is true? It's none of those, right? It's none of those. So it's got to be, we could only therefore be in this one. Does that make sense? We must only be in this one if we're assuming both of those things are true ones. So you see how I got to that fact? Okay, and based on that, I'm trying to show like that mortal is true. All right, there's only one case that I can be in. What is B? Oh, it was also true. So that's a proof, actually. That's a proof that is valid. I hope that makes a little bit of sense, at least. It's like, all right, we're assuming that this is true. Assuming this is true, go make a truth table, and let's just like look at all the ways that both of those are true at once, and look at mortal. Is that also always true? And it is. That's pretty nice. That's pretty cool. So that's deduction. It's kind of why it's easy to do in a computer, because like just like look at the table, build the truth table, computer. So that makes it easier. But it is still a good thing to learn, and now you know where like the real reason, logically, why valid it makes sense, right, in an argument. Any questions about that? That's pretty cool. It is something to think about for sure. All right. All right, a couple more things. So this implication thing, it's a new symbol, it's a new truth table. I told you that you can build any truth table, right? You can build up any answer out of just and or and not. I told you that. So can you make a circuit diagram for implication? Like you feed in a wire for A, you feed in a wire for B, then you do some fancy stuff. I don't know, a bunch of little smaller circuits, right? And it somehow spits out A implies B. Could you do that? You could, and here's how. You could use, which gates will you use? Here's the secret. This, if you think about it long enough, this is equivalent to not A or B. All right? Let me prove that to you very quickly. I just need to show that it's the same in every case. So not A ORed with B. So not A is false in this case. ORed with B, though, anything ORed with true is still true. So that's still true. Not A ORed with B. So false, ORed with false, that's still false. And then, all right, not A is true, right, immediately. And if it's ORed with anything, it doesn't matter, it's still true. So not A ORed with anything, right? In all of those cases, it's still true. So that actually gives me that exact truth table. That's pretty cool. So you can use a NOT gate and an OR gate, and you somehow made a circuit. You made a little tiny computer that does implication checking for you. Isn't that fun? All right. So yeah, that's kind of bringing it back to computer land. Yeah, I just have a couple more topics for the day. Let's talk about, it's called framing, but I accidentally said, I typed it wrong and it was farming the first time, so I've just kept that forever now. I thought it was very funny. So framing is what we're about to talk about. It is going to try and answer, like, I just have one slide. I'll try and answer this for you. Like, when you're making an argument, like, you probably watched the debate last night, maybe, if you're a political kind of person. And, like, the country is obviously very divided. So, like, you might be wondering this. Like, why can't this person see my point? It's so obvious that I'm right. Like, what's the problem? What's the disconnect? And here's the answer, right? So it's called a frame, short for frame of reference. It's like how you look into a situation, right? And so the frame of reference that you have as a human, it's going to shape how you view the world. A synonym for it is your worldview, all right? So it'll shape how you view the world and also all the assumptions that you are willing to make, all right? So this is a human problem. It's not like a logical problem. This is more like your worldview, all right? Your worldview. Whee. This is a very philosophical slide. It has to do with, like, not the denotations of things, because we all agree, like, what the dictionary says. It's more about the connotations of things. All right, and so I have a silly table here that I'll get to in a second. But, like, the idea is if you can control the frame of your argument, right? If you can control the frame, that will, like, you have won by that time. If you can be in control of somebody else's worldview, you can frame the argument in the right way, you have control over that entire argument if the the other person doesn't know about this, okay? So this kind of shows why somebody else who you think is very wrong, they can have the exact opposite viewpoint to you, and they can even go and justify it, which still doesn't make sense to you. There's still a disconnect, and it just has to do with that other person's worldview. The connotations of words. So like here is a very simplified like table that like has some topics that are hot topics in politics, and like ways that they're framed from people who are generally on the left side of politics and the people who are generally on the right side of politics, right? So I zoom in here. Hopefully you can just read this for a second and see, like, if you can control the worldview, like, these are what people kind of say in those groups, right? So if you can control that, you have won the argument, because then like that tells that just implies a lot of things, right? The second you use those kinds of words. So I hope that helps a little bit. So you can write the best argument ever, and somebody still won't believe you because it doesn't match their worldview. It's not an assumption they're willing to make. Things like that, which is kind of sad. I don't know. In a critical thinking class, we want like deductive logic to be king, but in the real world, sometimes that's not true. So yeah, hopefully you can see the difference here. The second somebody says one of those words is a very charged word, isn't it? So if you can control that, you've won your argument more or less already from the start. Any questions about that? Have we run into this problem before? No, a lot of us are young. We haven't gotten into politics too much yet, probably. Like this is a big deal. All right, please vote. All right, so let's talk about one last computer science concept for the day. Let's talk about state machines. So it's a fun little concept. I don't know if I'm going to program one for you. Definitely not today. But you can turn this into a program, and it makes like a beautiful program, in my opinion. Right? This is a way to break down computation. Like if you're given a problem, if you can break it down into this thing called a state machine, it just like gives you like the algorithm that you need to solve the problem. Remember that word. It gives you it, like it spits it out for you. Because we're always trying to write algorithms all day long, come up with one. So a state machine kind of looks like this. Like we're trying to break down computation, like do this thing, do this thing, do this thing, do this thing. And then if I did all those things, then I'll end up with what I really cared about, like my final answer. It's going to give me full credit on my assignment or like praise from my boss or whatever. So that's kind of your goal when you're writing a program. State machines are one way to break down a program. It doesn't always work out, but if it does, it leads to like a beautiful answer and an answer that's always going to be like usually correct. It's hard to make it incorrect. All right, so here are two drawings that I stole from the internet of what are called state machines. And they're just like, they're circles and arrows, honestly, but you can program these, and it gives you a lot of very nice guarantees. All right, so the idea of a state machine, before I zoom into these, is you're always in some kind of state. All right, like the state of your program, you're in one state or another, and then the circles are states, and then you can move to new states with arrows. Those are called transitions between states. All right. So here's like a very simplified view of, I don't know, a very boring person. So there's always a concept of where you start. Like when you're born, what state do you start out in? Like when your program begins, what state do you start out in? Let's say that this person, we're modeling a person right now, a boring person. They start out in the home state. So that's where they are, all right? And you can move around using these transitions to get to other states. Like maybe it's time to go to work. And so they would like to move to this work state, right? And so how can they get there? They are forced to follow this arrow, right? That's called the transition. And that means, all right, if I'm going to go to work from home, I need to follow this arrow, and that means I need to take the train, okay? Let's assume. So now we're in the work state, okay? And now it's time to go back home from work. We only have one option, right? We have to take the train back to get to home. Do you see how you're kind of spelling out what you can do? And that also is implicitly saying what you cannot do. That's very, very, very powerful. You can program this. So now we're back to the home state. Now it's bedtime, so we want to go to the bed state, and there's only one way to do that, right? To get from here to here, we must follow the sleep transition, okay? Those are the words. And then, like, we wake up, and we can do it all over again. So, like, do you see how, like, we're kind of forced to move around in this way? And that's very, very powerful if you think about it, because it's telling you what you can do. You cannot sleep at work, because that would imply an arrow from here to here, and there isn't one. You see that? That's very, very powerful. when you're writing a program. It's like a whole bunch of bugs that were possible cannot be possible if you make it this way. All right. So that's the thing. You can keep following them in loops. Like you can be like, maybe it's the weekend. You'll wake up and go back to sleep twice before you go back to work. That's the thing. It's just you are forced to move around in this way, and that's quite powerful. And let me show you a good example of how. So here's a silly little state machine for like a ride-sharing service, or maybe like an Uber or a Lyft app. So it's a slightly fancier state machine, but let me just like explain it in the normal way. So let's say that the starting state is this one. You have just requested that somebody come pick you up to take you somewhere. And so the very what you want, right, is to get to this state. Like somebody's coming to pick me up right now. But do you see, if we write our program this way, in order to get to here, we must pass through the payment stage. See how that's very important for the people who are writing the Uber app. This is making sure that you have to pay before you actually get a driver assigned. If you program this, it's impossible to get here without getting here. That's very, very cool, right? So like you request your trip, it's going to go to the payment. You're going to follow the payment requested transition to go to the payment stage, and hopefully it all works out. If the payment succeeded, only then does a driver get assigned to you, because then they know you're good for the money. Yeah, that's very powerful. It's making sure you've paid for your trip. If somebody programs it this way, there can't be a bug to get you from here to here without paying. If your payment fails, you got to go back to step one, enter a new card, and try again. Yeah, and then like you're in the driver's seat. The driver could cancel on you, like you're too far away or something. Then you also have to try again. Or if like the driver comes picks you up, you take your trip. You follow the trip complete state transition to right now the driver is back and assigned. Then you go to like the trip end state or something, and like it tells you to rate the person. So that's a state machine for Uber almost. Does that kind of make sense? And that's enumerating all the different ways that you can move around. You can pretend this will turn into a program, and you can prove. It's very easy to prove just at a glance that you cannot ever get in the car without paying. Isn't that so cool? You're forced to go in that way. You have to do that. So by writing down what you can do, it also tells you what you can't do. And that's beautiful, in my opinion. It makes it very likely that your program, if you write it like this, will be correct. Right? So, of course, not every program looks like this. But if it does, highly encourage it. Right? So here's kind of like the setup, right? So if I give you a problem to see if it works as a state machine, what you want to do is like you want to group your program into different states that your program can be in and different actions that move you across states. Those are your transitions, right? Those make a silly state machine for you as a student, okay? So as a student, I think of you as a simple two-state machine, right? You have two states when you're in this class. You have a learn state and you have a practice state, okay? So there's a concept of where do you start. I haven't given you any homework on the first day of class. So you start out when you first came here, you were in the learn state as a student, okay? And then you're just going to keep on alternating as I like give new things, right? If I assign an assignment and the class is over, then you're going to go to the practice state. You can stay in a state. If your assignment's not done yet, you're going to stay in that practice state. Keep on working on it, right? But then when it's time for a lecture again, you're going to transition back to the learn state, and then hopefully you're going to keep learning as long as you're here. And yeah, you just move around in that way. Does that kind of make sense? So you can stay in the same state. You can have self transitions like this. And there's also a concept of a final state. So if you put an extra circle in your circle, that marks what's called a final state. And that's where you want your machine to end up. So this is the only valid final state for you, my students, because on the very last day of class, you're going to take the final exam. And I have nothing left to teach you. You're not in the learn state anymore. You're just practicing, and then you leave the class forever. Does that make sense? So yeah, it's pretty interesting, state machines. So let me show you something cool that you can do with state machines that would just be very hard to program otherwise. So this is actually what I was taught. This is an algorithm that I was taught in my first programming class in college. So I'm passing along the knowledge to you. Okay. I'm forcing you to use this example because it is a very good one. So it's a state machine that will count words in a string. Let's pretend we have some sentence that was given to us. We can count all the words in that sentence, and it just works out very cleanly if you use the state machine. Right? So here's the idea. Let's say that we're in Scratch, and we get a sentence. We ask the user to type a sentence, and or maybe even a paragraph, and we will count all the words for them that were in that paragraph or in that sentence, all right? And so in our answer variable, we're going to get some sort of string, right? That's the fancy term. And let's say that we want to count all the words, and just to make it difficult, you might imagine like, okay, this is such an easy problem. I don't need a state machine. I could just count all the spaces, right? If I just count all the spaces, then like spaces separate words, then I just add one, right? It's like, hello world, there's just one space, add one, now there's two words, right? But that won't quite work out, because what if you want to use multiple spaces in between your words? If that's fine for you, that will mess up that idea, right? So maybe your sentence was hi mom, and those things are spaces, right? So a bunch of weird spaces, and we would like to count, that's what we got within quotes, and we'd like to count up all of the words in this string. Okay, so what we're going to do is we're going to read each character one by one, and we're going to run each character through our state machine that we're about to write, right? And we're going to hook into a count variable. We'll of course start at 0 because we haven't seen any words yet, and we'll just keep adding to count along a very certain transition. It will be very important to pick that one correctly, all right? But yeah, the key idea in the back of our minds is that, all right, spaces or tabs or like pressing enter, that's called white space in general in a computer. So white space, it separates those words one way or another, some amount of them, all right? Some amount of white space separates every word, and then every character, because we're going to shove every character through the state machine to transition it, every character is either part of some old word or the start of a brand new one, okay? If it's a non-white space character, right? So here's the state machine. You're either, as you're reading these characters from this sentence, you're in one of two states. This is how we're going to do it. You're either in the outside of a word state, or you're in the inside of a word state. So hopefully you can agree, like, this is a non-trivial problem. I don't know how to solve this problem by just like counting spaces or something. It's not good enough. This will be a very clean answer, right? So you're either in the outside of word state or the inside of word state. And at the very start, like, you haven't read any characters in yet, so we're going to start in the outside of a word state. I hope that makes sense, right? And then we're going to transition based on the characters that we see, all right? So if you saw a space character, right, that's the first character we see. If you see a space character when you're outside of a word, you stay outside of a word. You're still not in a word yet, right? You see the space character, you see even that space character. If you keep seeing space characters and you're not in a word yet, you're still not in a word yet, okay? So you're out. If you see a space, so we're going to show it. We're going to use every character. We're going to run it through our state machine. So we started here, we saw a space, still outside of a word. Saw another space, still outside of a word. Saw another space, we're still in this state. We're still outside of a word. Does that make sense so far? That's going to be the trick. And then we see our H, right? We see an H. Let me use, oh gosh, didn't want to do that. Let me maybe use my mouse to do this properly. Here. Let me draw a nice green arrow, and I'll just keep moving it. So, all right, we were here. Then we see the H. We see the H, and all right. That's right. If we see a non-space character, we're in a word now, aren't we? And we were here. We were outside of a word. So we should go and transition to the inside of a word state, huh? So you see a non-space character. Now we're in the inside of a word state. So now we saw that word. We're inside of a word now. Yeah. Then you see the I, and we're still here, right? We're inside of a word. If you see the I, still see a non-space character, you're still inside of that same word, right? So C non-space. And then, all right, I see a space. I'm not in hi anymore, right? So if you see a non-space when you're inside of a word, you're back outside of a word. And then, all right, now we're in outside of a word. We see M. That marks the new word, mom, right? So now we're back into inside of a word. We see the O. We follow this transition. We're still inside of a word. We follow this transition, M. We're still inside of a word. We see the exclamation point. We're still inside of a word, right? It's not space. And then we see one space at the very end, and that transitions us to the outside of a word state. All right. So the question is, when should I be adding to my count? When do I discover a new word and I need to count it? It should just be one of these transitions. Do we see which one it is? Which one of these notices a new word? So we start out outside. We're still outside, still outside, still outside. It was whatever we followed when we got to that H, right? Because that's what notices that brand new word. If we were outside, 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 which one was it? Which one moved us to here? There's only one. See it? It's just seeing a non-space character being outside of a word. That is what notices a brand new word, and that tells us to add one to our count. So every time we follow this transition, if we just remember to increment our count, that will do it. All right? And that's the secret. That's the state machine. It will work for, even if the user wants to put 5 spaces between every word, it will always work. Right? So you start out outside of a word. So here we are outside of a word. We run it starting with each character, right? So shove in the space character, we're still outside of a word. Same with the next one, right? Another space character, still outside of a word. Another space character, we're still following this transition outside of a word. Oh, we saw the H. Ooh, that was a non-space character. Now we're inside of a word, and also we want to add one to our count. See how that's going to keep track of which words we've seen? And we don't want to double count, so when you see the I, it's like, that's this transition. We're still inside of a word, but it's an old word we've already counted. Yeah, that's the goal. And then you see the space, and now you're in between words again, you're outside of a word, and this works for as many spaces. It doesn't matter, because we'll keep following that transition. But we were outside, we saw another word, we saw the start of mom, and so we got to add one to our count. The O, the M, the exclamation point, right, they're non-spaces, so they keep us there. And then we got one last character, space, that took us from here to here. We're in outside, that's our ending state, right? It's our final state, I guess. That's where we end up. And our count holds the correct count of all of the words. And so that is it. That's the answer. Does that kind of make sense? Think about how you might program that. Look at each character one by one. I hope it makes a little bit of sense. But that's the secret, and that's like what Google Docs, that's what Microsoft Word, that's the program, that's their algorithm. Essentially running that state machine to count your words properly, regardless of all, if you're the person who presses 2 spaces after every period versus just 1. It'll always work. I think that's very fun and very powerful. Any questions about any of that? All right, I think that is all that I wanted to do today. So that is that's the lecture for sure. Let's see if I need to give you something. No, it was just the lecture for the day. Everything else has already been assigned. So yeah, that's all I got.